Welcome back to the Chem OG and welcome to another edition of Strategy Monday. Today we're going to take a look at how it is that we can do pH calculations when it comes to weak acids and weak bases. So for strong acids and bases, they have very predictable behavior. So a strong acid produces however many protons as there are number of moles. A strong base produces however many hydroxides as there are a number of moles of base. But usually where things hit a speed bump is when we're talking about calculations with respect to weak acids and weak bases. And the reason for that is ice tables. And so if you're familiar with ice tables, you're probably familiar with not liking them so much. And that's because ice tables are repetitive and they always involve the same steps. So if you're unfamiliar with ice tables, the idea is to sort of chart what it is that's going on. We're going to write down the initial concentrations of our species. So that's the I part. The C part is keeping track of the changes based on the stoichiometry, and the E part is incorporating those values that we get into the equilibrium constant. So when we talk about weak acid and base calculations, that's what we're going to put down, an ice table. But this is Strategy Monday. I'm not going to talk to you about no ice table. What we're going to talk about is ways to avoid this repetitive ice table. So let's take a look at what it is that is involved in the calculation after everything is said and done. And so what we're doing is we're going to calculate, or we're going to take a look at the Ka expression if we're looking at an acid. And when we do get done with our ice table, here's what we're going to have. We're going to have x squared divided by the concentration of weak acid after we get rid of a whole bunch of things and we do a whole bunch of approximations. And if you've done ice tables, you know exactly what I'm talking about. So if we're just getting down to business here, and we need to solve for x. When we do solve for x, we're going to cross multiply, and we're going to cross multiply the Ka times the weak acid concentration, and we end up with this expression. And if we're going to solve for x, we're going to need to take the square root. Okay, so x is going to be the square root of Ka times the weak acid concentration if we're talking about an acid dissociating in solution and giving up a proton. And so x, the variable that we're solving for, is just the proton concentration. And if x is the variable for which we're solving, and that turns out to be the proton concentration, in order to figure out the pH, we're going to need to take the negative log of that value. Okay, so that's kind of how it goes down. And so let's talk about ways in which we can just do the steps without having to go through the steps, like having a one unified equation that allows us to pull all those steps into one. Before I do that, though, I want to talk about this whole square root business, because the number underneath the square root here is going to be some number in scientific notation, or 10. It's going to have a 10 to the power of something inside. And just to remind you, the way that square roots work is that when you take the square root of a number with an exponent, what you do is you take half the exponent. So the square root of 10 to the 12th, for example, is 10 to the 6th. The square root of 10 to the 8th is 10 to the 4th. Whatever number we have, we're just going to take half of that exponent, and that gives us our square root. And the reason that works is because, well, 10 to the 6th times 10 to the 6th is 10 to the 12th, right? And 10 to the 4th times 10 to the 4th is 10 to the 8th. When we multiply a number by itself, we're doubling the exponent. Taking the square root is the inverse of that, so we need to take half the exponent instead. All right, so here's the rundown. We're going to cross multiply the Ka and the weak acid, which we've already talked about. We're going to take the negative log, which we also talked about. And when we take a square root, we take half the exponent. So we're going to take that negative log value and we're going to divide it by 2. And that's it. So the idea is to take all those different things that we repeat over and over again and just be able to just cut to the chase and summarize them. So the Ka and the weak acid, if you have a weak acid in the problem that you're trying to solve, you'll be given the Ka in some form or fashion. You'll also be given the starting concentration of that weak acid. So these two numbers are ones that are going to be given to you. And then you're going to take the negative log, and then you're going to divide by 2. So let's take a look at that in a practical sense. So what if we're trying to calculate the pH of 0.3 molar propanoic acid, and we're given that the Ka of propanoic acid is 1.3 times 10 to the negative 5. Well, the first step is we're going to take those two numbers that we're given and we're going to mash them into each other. We're going to multiply the Ka times the weak acid concentration, and when we do that, I'm going to get 1.3 times 10 to the negative 5, and I'm going to multiply that by 0.3, and I get 3.9 times 10 to the negative 6. The next step is to take the negative log. So when we take the negative log of that number, we come up with 5.4. Next thing we're going to do is we're going to divide by 2, and we're going to get a pH of 2.7. And then the next step after that is, actually, no, we're done. Okay, so no need to set up an ice table, no need to do anything like that. Take the two numbers you're given, multiply them by each other, take the negative log, divide that by 2. And we're done. So here's another variation on the same topic. What if we're given a base instead? And so let's say that we're looking at ethylamine. Instead of being given a Ka, we're going to be given a Kb. And the concentration that we have is more or less an indication of how much hydroxide we produce as opposed to protons. So whenever we saw Ka in the previous problem, we're going to replace that with Kb. Wherever we saw pH, we're going to replace that with pOH. Whenever we saw the concentration of weak acid, we're going to replace that with the concentration of weak base. So the first step isn't Ka times the weak acid. In this case, it would be Kb times the weak base. And so I'm going to take those two numbers that I'm given, 6.4 times 10 to the negative 4, and I'm going to multiply that by 0.05, and what I get in the end is 3.2 times 10 to the negative 5. And then I'm going to take the negative log. When I do take the negative log, I'm going to end up with a number that's close to 4.5. When I take half of that number, I'm going to get 2.25. But because I was talking about Kb and the weak base concentration, the value that I just calculated isn't the pH, it's actually the pOH. Okay, so the value we calculated is actually the pOH and not the pH. So to be able to find the pH, well, pH and pOH together add up to 14. So I'm just going to take that 2.25 and subtract that from 14, and the number I get in the end is 11.75. So if we're taking a look at the equation for the acid and the equation for the base, here's what we get. For weak acids and bases, the way we're going to calculate either the pH or the pOH is to do the following. If we're given an acid, the pH is going to be equal to the product of the Ka and the weak acid concentration. And again, those are the two numbers that you're given in the problem anyways. You're going to take their negative log and you're going to divide that by 2. If you're given a base instead, you can calculate the pOH as the negative log of the product of Kb and the weak base and divide that by 2. And if the question is asking you for the pH, we'll make sure you subtract that number from 14. Happy Strategy Monday.